Okay, so we talked about sets. We also talked about finite set, you know, infinite set. For the infinite set, also include countable and uncountable, right? We also talked about a couple of theorems about the countable set. So, for example, any subset of a countable set is countable. Any superset of an uncountable set is uncountable, and also, the Cartesian product two countable set is still countable, and also the union of the countable set is also countable, right? So we talked about that in the previous videos. So now let's look at some examples. So this is one of the examples. In one class, we have 12 students wear black shirts, and 7 students wear white shirts. Okay, and 5 students they wear black shirts and red shoes, and also 4 students wear white shirts and red shoes. Okay, so the total number of students wear white or black shirts or red shoes is 22. So the question is, how many students wear red shoes? Okay, so that's the question. Well, how do we do that? Well, this problem we can have 2 approaches. The first approach, we can to use some assumption to denote in terms of the cardinality, and also use this inclusion-exclusion principle to handle that. So let's use the first way. So assume the cardinality of students who wear white shirts is 7, right? As you can see, the black is 12 black shirts, and then the students who wear black shirts and red shoes, so black shirts and red shoes is 5. Okay, students who wear white shirts and red shoes is 4. Okay, that's what we have. Well, we actually has one more information that it didn't tell us directly, but we can know, or we know. What is that implicit information? Well, do you agree that if a student wear a white shirt and then he can't wear a black shirt, right? So basically what we can get is it is 0. Okay, it is 0. And also, one more information is the total number of students wear white, black shirts, and red shoes, 22. So that means union R equal to 22. Okay. So based on the inclusion-exclusion principle, union B, union R, remember, equals cardinality plus B plus R, subtract W union B, subtract W, intersect, right? So intersect R minus B intersect R, and also plus the W intersect B intersect R. Okay. So you see left side is 22, W is 7, B is 12, right? We're looking at this is what we're looking. W intersect B, it's 0. W intersect R is 4. B intersect R is 5. And also, the intersection of W, R, and B, do you realize it's also 0, right? Because since W intersects B, it's already 0. So put all together, we have 22, this is 19, minus 9, so it's 10. It's R. So easily we can figure out that we have 12 students who wear the red shoes. Okay, that's one way to do that. The other way, we can also use this Venn diagram to do that. You know, if I draw those three sets, and apparently you can see that the middle one must be the student who wear the red shoes, right? Because the intersection between the white and black shirts are empty. So this is white. Oh, this is black. Okay. What we can tell? We can tell that is this part. The total white, what do we have? It's 7, right? The black is 12. The B intersect R here is 5, right? W intersect R is 4. So you can see that right now this is going to be 3. This is going to be 7, right? Well, we know that the suppose we call this part is called X. So do you agree that it's 3 plus 4 plus X plus 5 plus 7 equals actually 22, right? So we can solve that. So this is 7 plus this is 12, right? Plus 5 is 12 and plus 7 is 19. So easily we can see that X equals 3. So this part is going to be 3. So hence, if you read from here, you can also derive that the cardinality of the R. It's a 4 plus 3 is 7 plus 5 is also 12. Okay, so two ways. One is using the inclusion-exclusion principle. The other is using the Venn diagram. Okay, so that's the first example. Second one. Now this is some examples I want you to practice a little bit more. It is ask you to so this is a relationship about A, B, and C, and I want you to draw the Venn diagram and also sheet the area for those three sets. Okay, so let's do one by one. Okay, so B intersect C, it's this part, right? It's this part. So B intersect C, it's these pieces. And then if we have a union that, so do you agree? This part stands for this, okay? And then second, B intersect C, okay, is here, right? And then we have the A subtract of the pieces. So do you see that gonna give us is right, because it subtract this area. That's and part B. And then we can draw it here. A, B, and C. So B intersect C is right here, right? And then it's complement, right? It's complement, and then union A, okay? Union A. Basically, as you can see that, so this is the B intersect C and complement, right? So only this part, right? Only this part. That's it. And then you have a union A. So do you agree you need to put it here? Basically, is everything except this little pieces. So that will do the work. Okay, that will do the work. And okay, that will do the work. Cool. So let's do another simple one. Is using this Venn diagram to verify the these two properties. Okay, these two properties. So let's take a look. And first one is A equals A intersect B union A subtract B. Okay, so this we can have two cases, right? Either this is our A, this is our B, right? Or we can do like this, right? We can do like this. I mean, either way, we're going to verify that. For the first case, A intersect B, actually it's empty set, right? Because those two are disjoint. So this is the case A, B disjoint. This is the case A, B not disjoint, right? So if A intersect B is disjoint, so this part is empty. So A intersect B is an empty set. A subtract B, actually it's still A, right? Because it says that it's every element in A but not in B, right? So it's still A. And then so the empty union A is still A. So this one's good. Alright. And actually you can see this is empty, A subtract A, so it's just a still itself. Okay. Now you know the Venn diagram. If A and B are not disjoint, so this is the situation. A intersect B, it's this pieces, right? And then A minus B, do you agree that it's going to be this pieces? So if those two are union, do you realize that it's going to give us is A, right? It's A. So that's easy to evaluate. Same logic for this one. If those two are disjoint, A union B, it's exactly the cardinality of A union B is exactly the cardinality of A plus cardinality of B, right? Because this part is going to be 0. There's no element in common this year, right? For this situation, similarly, so A union B, the cardinality, it's all the elements inside here, and then it equals the cardinality of A, you count all elements here, plus the number of elements in B. But keep in mind that, remember, we counted this intersection part twice, so we have to subtract once, so that's minus. That will also do the work. Okay, that will also do the work. So that is yeah. That's how do we handle that? Okay, so that's meanwhile, this is also another very useful equation. So A equals A intersect B union A subtract B. And also don't forget that the A subtract B equals A intersect B complement. Okay, so A subtract B equals A intersect B complement. So those are very, very useful equations or relationships that you can use in further problems. Okay, so I'll stop here, and thank you for the watching, and I'll see you soon.